Hello everyone, I am Sunaina from the Department of Physics and Astronomical Sciences, Central University of Himachal Pradesh. I am a first year PhD student under the supervision of Professor Bhakchan Chauhan, and today I am going to talk about a fascinating topic, standing model of the particle physics. Understanding the fundamental building blocks of the universe. The topic which I am going to discuss in the presentation is particle physics, standing model of particle physics, about front-running leptons, about quarks and leptons, and about forces and about Higgs particle. So first of all, I start with what is particle physics. So the study of the individual particles like protons, neutrons, and electrons, which are called as the fundamental building blocks of the matter and the interaction between them. There are some questions that motivate us to study the particle physics, like are the fundamental constants of matter in the universe? If so, what are they and what are their properties? What are forces? How are they transmitted? What is mass? What is antimatter? And where did it all go? What does this tell about the origin of the universe? So, what does the phrase standard model mean? The standard model is a very successful theory which describes the three of the four fundamental interactions as the four fundamental interactions present in this universe, like strong force, weak force, electromagnetic force, and the gravity. But the standard model only explains three forces and the elementary particles that take part in these interactions. So, as you see here, in this chart, these purple ones are called quarks, and these green ones are leptons, and these red ones are the force carriers, and H is the Higgs bosons. So as you know that in chemistry the elements are arranged in a table, we call that as periodic table. In the similar way, when the particles are arranged, we call it as standard model. Here you see that up and down are the first generations, and this is the second generations, and this one are the third generation. And look at here, and these quarks, and we can say that these particles concentrates combine to form a particles, and the standard model consists of total 17 particles. Next, at quantum level, these particles are categorized into two categories. First of all, fermions, and second one is bosons. The fermions are the matter building particles such like electron, and the bosons are the force carrying particles like the photon. Next, fermions. Fermions are the particles which obey Fermi-Dirac statistics and follow Pauli-Astronomical principle, and these are the these have half integer spin. Let me explain what is Pauli-Astronomical principle. No two particles with the same quantum number can occupy the same orbital position of quantum state simultaneously. Exactly like no two electrons in an atom can have same of quantum number, and these have half integer spin. Mathematically we can write it as 1 by 2 and 3 by 2. Standard model has 12 fermions, which is divided into two categories, lepton and quarks. Lepton has 6 places, and quark has also 6 places. Leptons as like electron, muon, tau, and neutrino also has 3 types: electron neutrino, muon neutrino, and tau neutrino. These so these all are called fermions. These have half integer spin value, and they have a sizable mass and the electrically charged. On the other hand, these are the neutrinos, muon neutrino, electron neutrino, muon neutrino, tau neutrino, which have very little mass and are electrically neutral. Now we talk about the second type of fermion, which are called as quark. As you see, up quark, down quark, charm quark, strange quark, probe quark, and neutron quark. Quark terms are called by the Murray-Gell-Mann during the formation of 2CD, which is called as Quantum chromodynamics. These are heavy particles behave like composite particles. So let me talk about the second type of fermion, which are quark. Quark form was called by the Murray Gell-Mann, also called as the quantum chromodynamics. These are heavy particles behave like composite particles forming series like octet, doublet and triplet. These combine to form composite particles like hadrons, and these quarks cannot exist individually because they have to bind with other quarks. As you know, up and down quarks are the lighter, some states are heavier, and top and bottom are the even heavier. Let us talk about the hadrons. Hadrons are either contain mesons and baryons. Mesons are a pair of quark and antiquark, and a baryon a pair of three quarks. Example: proton, which is made up of up quark and down quark, and a neutron, which is made up of one up quark and two down quarks. It has charge UCT up charm, and tau has quark charge 2 by 3, and BSP has charge 1 by 3.
Carrier particles, named after the physicist Satyendranath Bose.
Next is the bosons, which are the second category of the quantum particles. Bosons are the force-carrying particles. They obey Einstein's statistics, can occupy the same quantum state. They do not follow Pauli exclusion principle. This allows to mediate forces that binds them together. These are the bosons in the next we talk about the forces that mediate these charged particles. First is strong force, weak force, electromagnetic force, and the gravitational force. So these forces work over different ranges and have different strengths. All of four, gravity is the weaker and has infinite range, and electromagnetic is 1 time stronger than gravity. Strong and weak force has very short range, and these forces work at the subatomic level. Weak nuclear force is responsible for the radioactive decay, and three particles associated with the weak nuclear force: W0 bosons, W plus bosons, and Z bosons. W and the bosons. As we see, the magnitude of these forces are: this is strong nuclear force. Its magnitude is gluons, which act as glue and holds the neutron and protons together to form nucleus. And next are the weak force. As you know, the weak force, which is registered as the Z boson, electromagnetic force like photon, and gravitational force is supposed to be made up of graviton. As we know that the weak force, there are W, Z, and Z bosons. This force is responsible for the radioactive decay, and W and Z bosons are the force carriers in it.
Higgs boson, sometimes dubbed as the God.
Higgs boson, which is also called as the Higgs, which is also called as the gold particle. When the Higgs boson discovered, the Standard Model became complete. The Higgs boson, named after the Peter Higgs, who proposed it in 1964, and Higgs boson discovered in 2001 in LHC. Higgs has a spin zero because the Higgs field is scalar, and Higgs boson gives particle mass to the Higgs mechanism. Whenever the symmetry is break, then the Higgs field gives mass to the particles, and thus we know that how all these particles get mass. Let's talk about the limitations of the Standard Model. What are the limitations of Standard Model? It cannot explain gravity, which is explained by the general relativity. It does not unify the strong and weak electromagnetic forces, whereas it unify the electromagnetic and weak force to make electroweak forces, but it cannot unify strong and electroweak to make the then unified theory of the Standard Model. It does not explain why there are so many generations of the particles. It does not explain the disappearance of the antimatter of the universe. It does not explain the neutrino masses. Standard Model predicts that the neutrino is massless, but The neutrino has mass. It has no explanation of matter and antimatter symmetry. Next we come to the conclusion. Standard model is a powerful and successful theory. It is a key to understanding the universe at a fundamental level, and our standard model of a nuclear particle interaction requires a Higgs boson to break electronegative symmetry and give masses to the all elementary particles. In conclusion, we can say that standard model is a remarkable achievement in physics. It successfully explains the behavior of non-fundamental particles and the interaction through these of the four fundamental forces. It has stood up to declare of the experimental test and has predicted particles like the Higgs boson before they discovered. However, the standard model is not the final theory. It leaves out gravity, dark matter, dark energy, and cannot fully explain nuclear masses and the dynamics of matter.